Hi there, this is Simab Akhtar. Today, we'll dive into the fascinating world of spatial temporal kriging. Now, you might be wondering, what exactly is spatial temporal kriging? It's a statistical technique used to estimate or predict values of a variable over space and time. It's like a treasure map for data scientists, helping them to predict unobserved values based on observed ones, but with a twist. Instead of X marking the spot, we're dealing with a dynamic, ever-changing landscape of data. Spatial temporal kriging is not just an abstract concept, but plays a significant role in our everyday lives. It's extensively used in fields like environmental science, where it helps to predict air quality or rainfall over a specific area and time. Geologists use it to predict the distribution of minerals or oil reserves in unexplored territories. Epidemiologists use it to track the spread of diseases over time and space. It's an amazing tool that helps us make sense of our complex world. The beauty of spatial temporal kriging lies in its ability to handle the unique challenges of spatial and temporal data. This includes dealing with issues like non-stationarity, where the statistical properties of a variable change over space or time, and autocorrelation, where values at nearby locations are more similar to each other than those further apart. Furthermore, it's not just about the where and when, it's also about the how. How do we model the spatial temporal structure? How do we handle missing data or outliers? How do we validate our model and ensure it's giving us accurate predictions? These are some of the questions we'll tackle as we delve deeper into the subject. So, are you ready to unravel the mystery of spatial temporal kriging? Let's get started. Spatial temporal kriging, in its simplest form, is a statistical method used for predicting unknown values at unobserved locations based on observed data. Now imagine you're standing in a field and you want to predict the temperature at different points in this field. You could measure the temperature at a few points, but it would be impractical to measure it everywhere. This is where spatial temporal kriging comes in. It allows us to use the few measurements we have to predict the temperature throughout the entire field. Let's break it down. The term spatial temporal refers to the two components of the method, space and time. The spatial part deals with the geographical data, in our example, the locations in the field. The temporal part, on the other hand, handles the time-based data, for instance, how the temperature changes throughout the day. So, how does it work? Kriging essentially uses the concept of correlation. It assumes that locations close to each other are more likely to have similar values than locations further apart. This is known as spatial correlation. Similarly, it assumes that measurements taken at closer time intervals are more likely to be similar than those taken at distant time intervals, which is temporal correlation. Now you might wonder, what makes spatial temporal kriging so special? Well, by considering both spatial and temporal correlations, it allows us to make more accurate predictions. It's like having an extra pair of glasses that not only lets us see the field more clearly, but also allows us to see how it changes over time. In essence, spatial temporal kriging is a powerful tool that helps us understand complex data sets. It's like a bridge that connects the dots between observed data and unobserved locations, allowing us to make informed predictions. Now that we have a basic understanding of what spatial temporal kriging is, it's time to delve into its mathematical model. The mathematical model of spatial temporal kriging is quite sophisticated, but don't worry, we'll break it down step by step. Let's start by looking at the basic equation of this model. The spatial temporal kriging model is a linear combination of spatial and temporal covariance functions. In simpler terms, it's all about how data points relate to each other across both space and time. Now, what exactly is a covariance function? Well, it is a measure of how much two random variables change together. In the context of the spatial temporal kriging model, the covariance function tells us how much the value of a variable at one location and time is influenced by its values at other locations and times. The covariance function is a critical component of the model because it captures the spatial temporal dependent structure in the data. This structure is essential for making accurate predictions about values at unobserved locations and times. Imagine you're trying to predict the temperature in a city for a particular day in the future. The covariance function takes into account the temperature at nearby locations and times to make this prediction. If the temperature at these nearby points is high, then it's likely that the temperature in the city on the future day will also be high. But remember, the covariance function is not a one-size-fits-all solution. Different datasets may require different covariance functions. In spatial temporal Kriging, we often use a product-sum covariance function that combines separate spatial and temporal components. However, other forms can also be used depending on the nature of the data. And there you have it. We've just scratched the surface of the mathematical model of spatial temporal Kriging. We've learned about the basic equation and the role of the covariance function. This is just the beginning, and we're about to go deeper into the mathematical model of spatial temporal Kriging. Let's continue our journey into the mathematical model of spatial temporal Kriging. In our last scene, we delved into the basics of the spatial temporal Kriging model and its foundational elements. Now, we're going to explore spatial and temporal variograms and their importance in our model. Variograms are vital tools in geostatistics, providing a quantitative measure of the spatial or temporal dependence in our data. So, what are these spatial and temporal variograms? Think of them as mathematical functions that describe the degree of spatial or temporal correlation among the data points. The spatial variogram describes the level of similarity between data points as a function of their spatial distance apart. Meanwhile, the temporal variogram gives us a measure of similarity between data points based on the time difference. To calculate these variograms, we look at the difference in values between 2 points, square it, and then average these squared differences over all pairs of points at the same distance or time lag. This calculation gives us a semi-variogram, which we can use to predict values at unknown locations or times. Now, how do these variograms help us in spatial temporal Kriging? Well, they serve as the backbone for our predictions. By understanding the spatial and temporal correlation in our data through variograms, we can make informed predictions about unknown values. For example, if we know that the data points close to each other in space and time are highly correlated, we can use this information to predict the value at an unknown point. We would give more weight to the nearby known points as they are likely to be more similar to the unknown point. In essence, spatial and temporal variograms are the heart of our spatial temporal Kriging model, enabling us to make accurate and informed predictions. With this, we have covered the major components of the mathematical model of spatial temporal Kriging.
It's been quite a journey exploring the mathematical model of spatial temporal Kriging, hasn't it? We've navigated through some complex terrain, yet hopefully we've managed to make the concepts accessible and understandable. Let's take a moment to recap the key points we've covered in our exploration. We started off by introducing the concept of spatial temporal Kriging, a powerful tool in the field of geostatistics. This method allows us to predict values at unobserved locations based on observed data by incorporating both spatial and temporal information. From there, we dove into the mathematical model that forms the basis of spatial temporal Kriging. We saw how this model combines the principles of spatial Kriging, which looks at the correlation between data points in space, and temporal Kriging, which does the same over time. By merging these two dimensions, we create a more holistic and accurate predictive model. We also discussed the crucial role of the covariance function and variograms in this process. The covariance function measures how much two random variables vary together, helping us to understand the spatial temporal structure of the data, while variograms provide a visual representation of this relationship. Both of these components are key to building a robust and effective spatial temporal Kriging model. Finally, we looked at how this model is implemented in practice. We touched on how it can be used to predict a variety of phenomena, from weather patterns to resource distribution.
highlighting the versatility and applicability of spatial temporal Kriging. Reflecting on this journey, we've seen how a complex mathematical model can be broken down and understood, and how it can be applied to solve real-world problems. It's a testament to the power of combining spatial and temporal data, and the insights that can be gleaned from this approach. With this, we come to the end of our discussion on spatial temporal Kriging. I hope you found it informative and intriguing. This is Simab Akhtar signing off. Until next time, keep exploring.